So we come to the last topic. This is an important topic. I'm going to introduce you to the internal forces. Look at what we did. We looked at the introduction. We tried to understand what is a beam, what are the supports on a beam, what loads act on a beam, how do you make sure a beam is stable. We also looked at static determinacy. Then we looked only at deformation, and we said in a beam there are three types of deformation. You have deflection, visible, slope, visible. Slope is the slope or rotation is the slope of deflection. This is delta at any location x. This is theta at any location x. Then we said there's a curvature phi of x or phi of x. The Americans like to say phi, but I think phi is okay. So phi is d theta by dx. Look at this. This is like which is derivative? Slope is derived from deflection. Curvature is derived from slope. So it's like deflection is like a grandmother. Slope is mother. Deflection is granddaughter. We'll find a similar relation is there in forces, but we'll come to that later. For convenience, we look at deformations as female in gender for fun and forces as male, Purusha and Prakriti if you like. So these are internal forces in beams, shear force in bending moments. What are they? So we looked at external loads, external force and moments. We looked at support reactions. Support reactions are also external in the sense when you isolate the beam and remove the supports, you get reactions which are external to the load. But when you draw a free body, you can't make out the difference. Before we go into that, let me ask you a very interesting problem. We told you that life is all about understanding the behavior of systems. If a system is given a stimulus, it will respond. In some problems in life, we want to predict the response given a stimulus. The doctor has an inverse problem. When you fall sick and go to a doctor, he looks at your symptoms, he looks at your response and tries to figure out what caused it. So you can have both kinds of problems. Stimulus causing response and finding out, knowing the response, what is the stimulus. Okay, so you have a system and let's talk of something very simple. A tension which you may be doing in the lab. Let's say there's and I apply an actual force on it. Okay, I put it in a machine and I pull it. Let's say its original length is L and it has an elongation E. I apply a force P. Is it clear? I'm doing a simple tension test on a steel rod. Now there are so many of you in the class. I want you all to learn. So I don't want you to copy, I don't want you to repeat, so I make sure each one of you gets a different bar. How do I ensure that? I change the lengths of the bars and I change the diameters of the bars. Some bars have small diameters, some have large diameters, some are short, some are long. Is it clear? And I make all of you do the test and I make you all draw a graph, and nowadays you have machines which will plot it instantaneously of the force applied, the tension applied, the tension induced and the elongation. Is it clear? The bar is elastic, steel. So if you do the test properly and the bar behaves properly, you are expected to get a straight line passing through the origin. Agreed? First, I've got 60 students out there with different lengths and diameters. We'll all get the same line. We'll all get the same line. What's your guess? You will get different lines. You will get different lines. You will get 60 lines. Okay, because the areas are the same, are different, and the lengths are the same, but the material property is the same. You will get different lines. You will get 60 lines. I'm just showing 5 lines here. So many lines. Okay, let's move slowly. Some lines have a steeper slope, like this line is steep. Some lines have a shallower slope, right? So we call the lines with steeper slope as stiffer. The structure is stiffer, the rod is stiffer, it's more difficult to stretch it, whereas this is more flexible. So some geometric properties making it. So which bar, when will it steeper? When the length is more or less, when the diameter or cross-sectional area is more or less? Tell me that. So answer this question. The stiffer bars are likely to be longer or shorter. You have to just say longer or shorter in your answer, or more area, less area. The stiffer bars, these lines, will you get when the bar is longer or shorter, or when the diameter is more or less? I think the answer is simple. You make make it very long. When you make it very long, obviously it's going to pull more. If you make it very short, very difficult to pull. So shorter bars are stiffer. You increase if the bar is very stout, again very difficult to pull. If it's a wire, easy to stretch. So more area also is stiffer. So that's an easy answer. High area of cross section, low length will be stiffer, and low area and high length will be. Now I want to ask a question. I want to make you all understand the power of science. Something is common to all these bars. They are made of the same material. How do I make all of you do some simple calculation, redraw the graph, so that instead of getting 60 lines, I get only one line? What should I make you do? You've got the calculations, you took the readings for different loads, you got different elongations, you got the table of P and E, and nowadays you can, in an Excel sheet, you can get the. Now I want you to do something to your graph, your y-axis and x-axis, so that all students get the same line. This is science. Obviously you've got to do something which will neutralize the differences in the cross-sectional area and the length, and which will bring out a property, a beautiful material property hidden in all the bars. What should I make the students do? How do I show what is common to everybody? That is science. That is synthesis of knowledge. That means the appearances are deceptive. It looks like all the bars are different. They're not really different. There's something common in all of the bars, just as there's something common in all of us. What is common? It's easy to see differences. It's difficult to see unity. What to do? Any answers? X-axis should be what? Y-axis should be what? And then all 60 lines will converge to one line. I'll give you the answer. Remember Hooke's law. Hooke's law, the material property is the same. So all you have to do is to get stress on the y-axis by making all the students divide the load by the cross-sectional area, and strain on the x-axis by dividing the elongation by the original length, and all of them will get only one line, and the slope of that line is called the modulus of elasticity. So we pulled out something here. This is fine as far as the actual members are concerned, but okay, something more we'll cover here. If you pull a bar and you cut a free body of the section, this is a free body, and you cut a section at x, you'll find that the internal force is a normal force, which you can write as P. P is tension here, okay? And the tension is constant throughout the length of the bar. At any location x, it's a constant tension. That's how you get, because P is here, the reaction P is there, anywhere you cut, you get only the same P. So you can draw an axial force diagram, just like you're going to draw bending moment diagram in a short while. This is how you draw an axial force diagram, and you can get the norm stress, and you can get the strain, which is constant. And you have modulus of velocity here, which is stress by strain. And you can get a relationship between them. Now, the internal force in an axial element, in a truss element, is an axial force which could be tension or compression, a normal force. In a beam, what are the internal forces? When this guy is sitting on that beam and you have a sagging curvature, what's going on? So let's look at that. His two little feet has two concentrated load is hang in the middle of the beam. Well, because of symmetry, it's obvious that you get equal reactions here, P and P, there's no horizontal reaction. Got it? Common sense. To see what's going on, let's paint some lines on this beam. We'll draw a series of horizontal lines and series of vertical lines so that we see how those lines change. And this is what's going to happen. You will find that the normal lines remain straight, and this is a great discovery. Plane sections remain plane. This is a fundamental principle we find in beams. Plane sections remain plane. They don't warp in bending. Now let's cut sections. Okay, to find out what's happening internally, you have to go internal. You have to cut a section in the mind of us and remove one part and look at one part. So we are looking at the left part, cutting a section here. This arrow shows we are looking to the left after removing the right part. And so you will find that because of the sagging, the top layers will tend to contract. There will be something pushing it, and the bottom layers tend to elongate. There is something pulling it, and you can resolve all these forces pushing to what is called a compressive force C, resolve all the forces which are distributed pulling it below and call it tension. This is the resultant, and this C and T are separated by a lever arm which I call Z here. So I've got a couple, a force couple hidden inside the beam when this load is applied, and so that is called bending moment. Okay, that is called bending moment, whose value is simply either C into Z or T into Z. The normal moment we talk of is an external moment applied to the beam. The bending moment is something hidden in beam, and it is generated the moment the load is applied because you cannot satisfy equilibrium otherwise. You can't see the moment. You can see only the curvature. You can see the deflection. You can see the slope. But without the moment, you won't get the curvature. Moment is needed for satisfying equilibrium. Now you can see here that if you take this force P and the lever arm A, that external moment P into A must be satisfied by the internal moment TZ CZ. That's equilibrium. So we've introduced you to the concept of bending moment. And if I take another section, now this section was cut in the middle. Now let me cut a section B a little away. You will find that in addition to bending moment, I get something else. In addition to bending moment, I get what is called a shear force. And the value of that shear force is P, and the shear force is distributed. The bending stresses, the normal stresses, bending moment is caused by normal stresses are distributed linearly. We'll see that shortly. Shear stresses are distributed in some other fashion. If you have a rectangular cross section, it is distributed parabolically. We don't have time to discuss shear, but we'll look at bending closely. So in this region between these two forces, you have pure bending, no shear force, but normally you'll have shear force. You'll also recognize you have a varying bending moment. We'll see that shortly. Some sign convention. You can have any convention, but one of the conventions normally followed is positive shear strain. Shear strain is caused by shear stress, and positive shear strain is when you see a movement like this. And typically when you show a force, a green arrow like this on the right side of your section, or a arrow like this on the see this section. See, for equilibrium, the green arrow must be either pointing downward or upward, right? Then only equilibrium is satisfied, then you have a moment also. So when the green arrows provide a kind of a anti-moment, you say it is anti-clockwise movement, you say it is negative, otherwise you say it's positive. So whenever you draw a section and you show and draw left to right and you put it downwards, that's positive. As far as movement is concerned, very simple. Sagging moments and sagging curvatures are positive, and hogging moments and hogging curvatures are negative. We've already seen that. We'll get to know this better when we actually do problems. Your first problem. We've already found reactions to this. You know the reactions VA and VB are WB by L, WA by L. We've discussed this at length. Now we want to know what's happening inside the beam. We know there are going to be shear forces and bending moments. We want to know how they vary, what are their values at any location. So what do? We take the free body. Free body means we remove the supports and draw this. We've got this free body. Now we start cutting sections. Okay, let's cut a section at a location X from the free end. So X is less than A. And when you cut a section, you're actually separating that beam into two parts. It's enough to look at one part, but you can also look at the other part, and when you join them, the internal forces will vanish. So when you look at the left part, you know clearly that, and let's follow a positive sign convention. This is going to point downward. This is positive shear, and there's going to be a positive sagging, which we'll draw like this. On this half of the beam, it will show up in the opposite direction because this is in touch with this. Newton's third law says each body, when it presses against the other body, will have an equal and opposite force. Does it make clear? Does it make sense? So either if I draw in the right part, my positive shear will point upward and my moment will point clockwise. This is sagging. If I'm drawing the left half, it's going to point downward and this way. Usually it's enough to draw one half. You need not draw. But whether you find the equilibrium by this half or this half, you should get the same answer. What is the answer for V of X? What is the answer for M of X? Very easy. Can you write down? V of X as for equilibrium sigma Fy equal to 0 must necessarily be plus WB by L. M of X to satisfy equilibrium must be this. This is forming a couple, right? This and this are forming a couple, so it must neutralize that couple. It will be plus WB by X. This answer will be the same whether you look at this half or this half. It's easier to look at this half. Got it? Now, if you want to know what's happening on this side, because this equation holds good from X equal to 0 to X equal to A. Once I go on this side, my equation is going to change. And again, I can look at this half or this half. Maybe it's easier to look at this half. I do the same thing. Something happens to my shear force. This reaction here, WB by L, is acting upward, W is acting down. This W is more than WB by L. So I need to have something pointing upward here. But upward here means negative shear by my shear convention. And so it is minus. My suggestion is we put this downward and write it as minus. Okay. So you write an expression for shear force and write an expression for moment. And when you plot them, plot these expressions on a graph, X versus V of X, you'll find a linear variation for bending moment and constant shear force, right? Okay, now you draw this first. Now, structural engineers don't want to draw axis. So as a beginner, we'll draw the axis first. We've got positive shear. Shear is constant in AC, it's WB by L. Shear is constant in CB, it's minus WA by L. You also notice the shear in this region is equal to the reaction here. The shear in this is equal to the reaction here, but with a negative sign. It's constant when you have a concentrated load. And we now will stop drawing x-axis, y-axis. This is what we call shear force diagram. Similarly, let's draw for bending moment. Bending moment, we know the answer is, see, it's linear it's linear here, WB by X, WBX by L, and it goes down here if you actually write this. So it's forming a kind of a mountain, straight line, and the maximum moment occurs where the shear force is changing sign. That's very interesting. So if you substitute X equal to A, this is linearly increasing, it is WAB by L. Whether you go from left to right or right to left, you'll get the same answer. This, again, we remove the axis, and that diagram we call bending moment. Okay, there is a relationship between shear force and bending moment. Very interesting. One is a derivative of the other. We can show that, but when this has a slope, and that's why this is constant. This also has a constant slope but negative, that's why this is constant negative. And that relationship we will see later. dm by dx equal to v. We'll prove it, but right now itself we can see the behavior in full flow. And the deflected shape is going to be something like that, sagging curvature. Let's now look at something that gives a hogging curvature. Cantilever with a load at the free end. So we've already got the support reaction, we've got the free body, you cut a section at X, you can either take the left part or the right part. Actually here the right part is more convenient if you don't want to calculate the reactions. Without calculating reactions itself you can get bending moment and shear force. You draw the signs the way we showed you and you get, it's very easy. See, this green arrow must be equal to P. They form a couple which has to be neutralized, and you'll find that you already got an anti-clockwise moment, you'll get this. But if you look at this part, it's very clear, P, P and P into L minus X, but it's hogging, so it's going to act. So we first draw the sagging moment. If it comes minus, it means it's hogging. And again, if you plot shear force diagram, P is constant throughout. Doesn't matter where you are cutting, you have so P, it's a positive shear force, but you have a negative bending moment diagram. Bending moment diagram is maximum at the fixed end, PL, it's 0 at the support. If you cut a section at 0 at the free end, if you cut a section at the free end, you get no moment. So again you see a relationship here, very interesting. The slope of this diagram is constant, and that's a constant shear force. dm by dx equal to v. Okay, and the curvature is hogging very clearly. We have time for one more. Do a moment. Concentrated moment, remember, don't get given by giving a couple. This is your loading diagram. It's very easy. You have only a moment as a reaction. There is no vertical force anywhere, and that's your free body. If you cut any section anywhere, you get only a moment. There is no shear force. The shear force diagram is easy to draw, 0 shear force. Bending moment diagram is constant throughout the length, it's called pure bending. Again the slope of this is 0, so you find that is getting validated, right? And this gives you, this has to give you a curvature like that. It's hogging. That's it. This is I'm speaking from IIT Madras. So the last screen is some pictures from our beautiful campus. You're all most welcome to come here anytime. I look forward to seeing you here as maybe our MTech, MS or PhD students, or maybe even faculty. Any questions? Yes? Now let's see the question. First question. What is the work of reinforcement in a beam? Okay, you've gone inside the beam. Till now, we talked of beam. The beam can be made of any material. The first beam that man used to step across a stream was a fallen log of wood. What is the material? Timber. Most materials, and you know that part of the beam will go into axial compression, part will go into tension. Timber is one natural material which can resist both tension and compression. Similarly, steel. Steel is, of course, you have to extract steel iron ore from the soil, from the mineral, and then manufacture steel beam. Steel also is equally good in tension and compression. But concrete or stone and most natural materials of its kind are strong in compression but very weak in tension. So you take concrete itself. So to make up for the poor tensile strength in concrete, we have to put some material which compensates and gives it the strength and in fact takes most of the tension. That is why we put steel bars embedded in concrete. Okay, so that is the role of steel reinforcement in concrete. That is the topic you should study in concrete. Now we are talking about any material. We are convenient assuming that the material is homogeneous, isotropic, elastic. Okay, so take steel, it fits our purpose very well. Take most metals, it works very well. But concrete also behaves in the same way, but it's a little more complex to see the detailed behavior. Why is beam considered a tensile member? No, beam is not a tensile member. Beam is beam. Tensile member is tensile member. Beam is not tensile member. Beam is when a beam, there is a plane in the beam which is not seen. We'll see in the next lecture that plane is called the neutral plane. That axis is called the neutral axis. When the beam bends in a sagging curvature, the top portions of the beam get compressed. So you could say the top portions are compressive members if you want, compression members. The bottom parts elongate. They behave like tension members, but they are kind of funny tension members. Normal tension members, a rod if you pull, the strain is constant at all points in the cross section and along the length. In a beam that doesn't happen. The tension is at the neutral axis, the strain is 0. At the extreme tension fiber, the strain is maximum, and there's a linear variation. So it's a tension which is varying linearly along the depth of the beam, and a compression which varies linearly along the upper region of the beam, linearly varying strains, linearly varying stresses. On top of that, if your bending moment is varying and not constant, then your value of axial tension and compression are also varying along the length of the beam. So certainly beam is not a tension member, a beam is a beam. But it's easy to understand beam behavior after understanding axial tension and axial compression. In addition to the normal stresses and strains that you get in tension and compression members, you also have shears which actually do a little mischief. Plane sections remaining plane is violated a little bit, you get a little warping. That's a secondary issue. Any other question? What is the physical significance of internal hinge in a beam? The physical significance is that it brings in, it makes the system just rigid. Just rigid systems have a lot of advantages in bridges. Most bridges in India are simply supported. That's why when you get into a bridge, you feel a bump because when the wheel goes over the bridge, the slope changes and you feel the bump. In a continuous bridge, you won't feel the bump. That's one indication. But continuous bridge is statically indeterminate. In the early days, man was afraid of constructing statically indeterminate structures because there are additional stresses that are induced by effects like support settlement, temperature and environmental effects. Unless you know about it, you don't design. So even today in India, most bridges are still simply supported. But simply supported spans become expensive when the spans are large. In a bridge, the span is large. You can't keep putting piers everywhere. Okay, you want to limit the piers. You want to have long span, 50-meter span, let's say. Then the depth of the beam will become large. Someone has to pay money for it. So the bending moments are very large, the deflections will be large. So the span to depth ratio is about 1 in 10. So you know, if you have 50 meters, 5-meter depth, you can't, it's not manageable. So you have to economize. How do you economize? The balance cantilever is a good concept. In the balance cantilever bridge, what do? We have a anchor span, we have an overhang, and we have a suspended span. So you have suspended span, 2 overhangs. That's a huge span. I can get 50 meters out of that. Not only that, my sagging moment is restricted to only the middle span, the suspended span. That span is small. The depth can be small. I can shape it well. But I have guarantee that it's like a child which can sit on the parent in the overhang, and when vehicles move, they don't feel any disturbance. There's compatibility maintained. Both will deflect the same. Both will rotate. Well, they won't rotate exactly the same, but that's how. So in my detailing, I must make sure that the child is resting on the parent. That's where the internal hinge comes. Now suppose there are support settlements. You will find that you won't get any additional bending moments due to support settlement. You know, the pier can sink, it's very heavy, the soil can move. So that's why you can solve large problems by intelligent design, but it's internal. I hope that answers your question. Why not consider the self weight of the beam in beam analysis? Excellent question. You have to consider. You have to consider. We will show it. In fact, your question is justified because we showed you problems where with concentrated loads. In the next class, we will show distributed loads where the self weight will come. But the reason why we don't show it in the early stages is bridges are designed not to take the self weight. Bridges are designed to take vehicular traffic on them. Buildings are designed not to take just a self weight. Self weight you have to design, you have to analyze for. It's very important. But it's easy to find the effects of self weight. It's more difficult to find the effects of what is called live loads which act on the beam. But your question is very right. We will look at the effect of self weight in the next lecture. Very good question. What is the main purpose of shear force? Shear is something that we don't want really. It comes on its own. It's an uninvited guest. The difference between normal stress and shear stress is normal stress, when you apply normal force, a rectangle remains a rectangle. Either it will elongate or it will contract depending whether the normal force is tensile or compressive. Shear distorts. The rectangle becomes a trapezium. But it's a truth. Most materials are weak in shear. There are failure theories based on shear. Shear is in a way a necessary evil. You can't help it. If I have a free body and I have a force acting here, just for equilibrium I need a force in the opposite direction, and that is normal to the axis of the beam. So you have possibly forces tangential, that those are our tension and compression, those which are normal. Those which are tangential to the normal surface, they are called shear forces. What's the purpose of the shear force? Shear, it has a purpose. Let me explain to you. We cut sections, the left section and right section. What joins the two sections together? It's the friction provided by shear. So shear is kind of friction. It's necessary. It's what hangs together beams. Without that shear, the beam will not be one beam. So you need the beam to connect the left half to the right half, and if you have a slip, you have danger. So shear holds together the different. It's done by friction. Now again, if you've studied physics, you'll find friction is a necessary evil. You won't be able to walk if it were not for friction. So that's the purpose of shear. Shear is what integrates a structure and makes a beam behave like a beam. Okay, good questions. Tensile reinforcement is absent in beam. What will limit the flexural cracks? I think these questions are coming from senior students. You are talking about questions related to reinforced concrete. Maybe we'll have a separate session on reinforced concrete. I don't want to confuse the young third semester students. There's no cracking. Otherwise they'll be afraid of designing beams. Our beams are not cracked. Okay, he's talking about cracks in reinforced concrete beam. There the reinforcement prevents the crack propagation. I've dealt with that. We won't return to that. Our third semester students should think of healthy beams which don't crack. They're nice beams, no cracking, no damage, good beam. Don't damage the beam. Don't damage the student. Next, which software is best to analyze structures? Your brain. Answer is very clear. The best software is your brain. Today, students graduate from colleges without knowing how to do a propped cantilever with an internal hinge. You need a computer to do it. If you want to build a house, you need a computer to do it. So, students learn to analyze and design with your hand, with your brain, master it, understand the physics, understand the mathematics, so that when you use the computer to solve big problems, because you don't want to waste your time, you want to use a machine to do it, you will develop the ability to know whether the answer that comes out very fast at lightning speed, whether it is right or wrong, whether your reaction should be upward or downward, whether your bending moment should be sagging or hogging, whether the result that you get minus 832.625 kilonewton meter is off by a factor of 10 or 100, whether that minus should be plus. So, your hardware is your brain, your software is the intelligence in the brain. Develop that. That's the purpose of education. No software at this stage, later. This is, we are giving you an introductory talk on but if you want software, use my software. That's a separate thing. That I'll give you later. Okay, next question. What is the relationship between twisting moment and moment? One word has got twisting in it, the other doesn't have twisting in it. Moment is a couple with a lever arm. That moment is a moment. When that acts on a structure, it can produce bending or twisting or both. Twisting moment is a word we use for internal moment in a structural element in a shaft. Bending moment is a word we use for internal moment in a beam. Got it? So, twisting moment is a moment, bending moment is a moment, external moment is also a moment. All are called moments. Next question. That's it. Thank you very much.